point are we using right now?
It is week 5.2. And we are in section 2.6 now.
Okay, thank you.
Not a problem. All right, cool. Now that I've got this working, that was weird. Today, we're going to be talking about section 2.6. 2.6 is all about this idea of the question, can we take derivatives of derivatives? Now remember, all we needed when we were taking a derivative the first time was for our function to be continuous wherever we were differentiating, right? So since our derivative computes another equation, as long as that other equation is continuous, sure, why not? As an example of this, let's consider the equation y is equal to 4x squared plus 3x minus 12. Well, for this, we know that y prime is equal to 8x plus 3, right? And we know the derivative of y prime is just going to be 8. Why don't we call this y double prime? Because this is continuous everywhere, right? It's not a problem. A constant function is continuous everywhere, right? So why don't we go ahead and take the derivative of this? Let's call it y triple prime. So sure, why not? As long as what you're getting out is continuous, yeah, you can keep applying the derivative over and over and over again. And what I should be saying here is continuous where you want to differentiate it at, right? So, for example, if we had, let's say y is equal to the absolute value of x, y primed then would be equal to -1 for x less than 0, and 1 for x greater than 0, and y double prime would be equal to 0 for x not equal to 0, right? Because this thing, it's continuous everywhere, but it doesn't have a derivative defined at 0, right? This thing's not continuous everywhere, but we know both sides of it will be 0. The derivative everywhere except at 0 will be 0. So y double prime would be 0 everywhere except at 0. Make sense what I mean? We just simply don't have a value at x equal to 0. Make sense? Now, on the notation of all of this, I want you all to notice the first derivative, y prime, second, double prime, third, triple prime, the fourth is in parentheses. It's 4 in parentheses. Anytime you see something like yn, this is generally, not always, but generally going to be the nth derivative of y. And I say generally because, yeah, I could give you some weird power like 4x plus 2, right? And that would be understood to be a power. But generally, just an integer, well, not even an integer, a whole number in parentheses like this will tell you that this represents a derivative. Does that make sense to everybody? Having said that, on some other notation, we've got dx or dy dx, d squared y, dx squared, so forth and so on, right? Now let's think about why that is. Y double prime is equal to d dx of y prime, which is equal to d dx of d dx y, right? So what this notation is doing is just condensing these two derivatives together. Make sense what I mean? So this comes out to be d squared dx squared y. Now these aren't really squares in the sense of them being squares. This is just the notation for this particular operator being done twice. That's all we're saying here. Does that make sense what I mean? Yeah, cool. So, just to reiterate the point I was trying to make just now, let's say I told you d dx of y is equal to 3x. The second derivative is not going to be 9x squared. That's not what this represents. This notation represents the second derivative. So instead, it would come out to be 3, right? So just be mindful of this notation because it is strange, but it has a very particular meaning. Having said that, reiterating this point about the prime notation, after the third prime, we started using these parentheses with a whole number value in them, just because who's going to sit here and count 4 primes, 5 primes, 12 primes, 100 primes? Like, that's not tenable. This is just a way of saying, hey, this thing is going to suck to write all these primes out, so let's condense that down. So, as an example, if we wanted to calculate the third derivative of this function g of t, we'd apply the first derivative, the second derivative, the third derivative, and then we wanted to evaluate it at t is equal to 2, so we throw 2 through. Nothing world shattering here, right? Some more on just definitions now. If we're given some position function, the derivative of that position function with respect to time is going to be velocity. And the derivative of velocity with respect to time is going to be acceleration. Now, out of curiosity, does anybody know what the derivative of acceleration is? Called jerk. And the derivatives after that would be snap, crackle, and pop. Not kidding, that is literally what the physicists decided to call it. just making sure, but y'all at home can hear me, correct?
Yeah.
Yes.
Awesome. I couldn't remember if I turned my mic on or not. All right, so in this particular problem, we're given Dude Buddy McGee's position function, right? And we want to know what the acceleration is and the velocity function is. They ask for at a particular time t is equal to 3. We're just going to find these functions. So we know the height as a function of time is equal to negative 16t squared plus 48t plus 160. So for whatever it's worth, what this equation tells us is that the guy starts at a height of 160, or my bad, the ball starts at a height of 160, is thrown up with an initial velocity of 48 feet per second. It is decelerating at a rate of negative 32 feet per second squared. I'll explain why this is 32 and not 16 in just a second. So we now know, based on that previous slide, that the velocity as a function of time is equal to the derivative of our position function well, this is going to then become negative 32t plus 48. And the acceleration well, it's equal to the second derivative of our position function, which is going to come out to be negative 32 feet per second squared. Just a general note, when talking about projectile motions, I don't have a smaller eraser, so this will have to do. When talking about projectile motions, the path that took looks like this, right? It's described in two parts. The x direction and the y direction. The x direction is generally just going to be some initial velocity times time, plus whatever your initial position is. So this is your velocity in the x direction initially. This is your position in the x direction initially. For the y position, it's going to be equal to 1/2 a times t squared plus by initial time plus d let me change those subscripts plus your initial position in the y direction. So looking back at this describes height, right? This is 1/2 at squared. So looking at this, you know automatically that the acceleration is going to be negative 32 feet per second squared. Does that make sense what I mean? That's how I knew just by looking at this what it was going to be. So I point this all out, not to give you a physics lesson, but because this lets us see a couple patterns that are going to show up throughout the class that will be useful for us to use. The derivative of this is always going to be AT plus VIY, and the derivative of this is always going to be just A. So as a pattern that we can check our solutions against. Our initial equation is of this green form, right? Our second equation, negative 32t plus 48. That's of this second form. And our final equation is just negative 32 feet per second squared. So as a check method, this is worth knowing. Get what I mean? Cool. So really quickly, comparing our solutions up here, the books, our derivatives all come out to be the same. And instead of beating a horse to death, let's jump to 2.7. Before I get much further, everybody at home, how does the board look to you?
It looks good now. At the beginning, you were a little too far to the left. Or you're right, I mean. Yeah, like we can't really see over there.
Gotcha. All right. So we're going to do a thing. Tell me when you can see the eraser.
Yeah.
Right here? Go.
Yep.
All right. Good to know. So jumping now into section 2.7, take heed of this message. This stuff is going to take some time to really understand and work with. And the reason why is because it's just different from the way we normally think. It's going to use the chain rule a lot. But what this section is all about is what's called implicit differentiation. Before we can define implicit differentiation, we have to understand what an explicit and an implicit function is. An explicit function is a function that says, hey, your function is defined by this variable in this very well-defined way, this very well-described way, right? So what I mean to say is y is equal to x in this particular way. So you can isolate y from all of your x's. Get what I mean? So it explicitly tells you how y relates to x. So I argue that this is an explicit function or an explicit equation. Why is that? Well, we can isolate y from x. If we divide both sides by x, we know that y is equal to 1 over x. And from that, we can find the derivative. Is everybody cool with this idea? So all an explicit form is, be it a function or an equation, So an explicit function and an explicit equation. Get what I mean? Like in both of these right-hand sides, there'll be no y's. It'll only be t or x or whatever your variable is. So as comparisons, an implicit function, or an implicit equation, I should say. It's not a function, it's an equation. Now notice, if you're going to solve for y here, y squared is equal to 4 minus x squared. So now we're going to apply the root, right? But when we do that, we're going to get two different parts. Now what's happening here? What's happening here is that after this point, there's two different possible answers given a single x value, right? We have the positive answers, we have the negative answers. This is going to form a circle centered on 1 of radius 2, right? So ignore the fact that this is a lopsided as shit circle. We're going to squint our eyes and pretend that it's not lopsided. What we've got here is this first equation up here. It's going to represent the top of our circle. And the second equation, the negative part, is going to represent the bottom part of our circle. So this is, again, an implicit form. Because even though y here relates to x, we have two different values. But really, we're stuck up here in this y squared form. This is just an understanding of what this y squared would be. Does that make sense what I mean? Yeah? Cool. So, how would you find the derivative of this? We want to find a line that's tangent to this circle. So we need to find the slope, right? You need to find the derivative. How are you going to do it? You're going to go to that bottom equation and be like, all right, let me find the slope for all of the points on the top, and then for all of the stuff on the bottom. No, that would suck, right? That would be crazy. So instead, you think, hey, I'm going to start here. Okay, you're going to have to do a bunch of work. Why not start here? I mean, the amount of work you're going to have to do in both cases will be about the same. So why not just go ahead and do the derivative here, and then do the work that you would have to do here? Make sense what I mean? Let's start here. So the first thing we're going to do, we're going to apply d dx to all of this. X squared plus y squared is equal to d dx of 4, right? Derivative of a constant is 0. And we can use the sum and difference rule here, right? So let's do that. We're going to get d dx of x squared plus d dx of y squared is equal to 0. Well, we know how to calculate this, but what about this? What do you all think? Hint, we're going to use the chain rule like that suggests. So if we think for a second of u as being equal to y squared, what we really have here is d dx of u, right? But by chain rule, didn't we see that this is really d dy of u times dy dx? Wasn't that a thing? So what we're going to get over here is 2x plus du dy. It's going to be 2y dy dx. Well, y is defined implicitly, so we're just going to have to leave it as dy dx. So this is what we're going to get. All right, so rewriting this. 2x plus 2y dy dx is equal to 0. What we've got here is this 2y is like du dy and this dy dx is just dy dx. And combined, this is like du dx. But we said u was equal to y squared. Making sense? So what do y'all think of this so far? Is it making some sense? What we're doing is anytime we see y and a bunch of stuff being done to it, we're thinking of that as u. And then we apply the chain rule. We're like, okay, well, first thing I'm going to need to do is apply the derivative of u with respect to y, and then multiply that by the derivative of y with respect to x. So in doing that, what we're going to get is this 2x plus 2y dy dx. But we want to know what the slope is of all these tangent lines. So now we have to solve for dy dx. And what this tells us is that 2y dy dx is equal to negative 2x. So dy dx is equal to negative 2x over 2y, or negative x over y. Is everybody cool with this? So now we have an equation for the derivative. So we can go ahead and find slope-intercept form now. I mean, we can find the equation for the tangent lines. Is everybody cool with that? Yep. Awesome. So throwing out some examples. We've already done an example similar to D. Let's look at B really quick. Let me take that back. This really isn't all that similar to D. Let's look at B first. So we're told that we want the derivative of 2y cubed. That's it. Yep. Well, by multiplication of a constant, we can pull out that 2 right away. Yeah? Let's do that. It's 2 d dx of y cubed. Now let's take a moment to observe that u is equal to y cubed So doing that, we're now going to find that this comes out to be 2 du dy dx is equal to 2 3y squared dy dx. Or 6y squared dy dx. Now in the second case, in the case of D, we're going to have to apply the product rule. D dx of xy squared. Well, by product rule, we know this is going to come out to be y squared of d dx of x plus x of, or x times d dx of y squared. Right? All I've done here is applied the product rule. Well, this derivative is going to evaluate out to be 1. Agreed? And here, we need to recognize that y squared is playing the role of u. Right? So with that, we're going to get y squared plus x times du dy du. I mean dx, my mistake. Well, according to this equation, if u is equal to y squared, du dy is going to come out to be 2y. We're going to have y squared plus x times 2y dy dx. Because u is equal to y squared, du dy is going to come out to be the derivative of u with respect to y, which is just going to be 2y. Is everybody cool with this? So what are we doing here? We're applying chain rule. We're saying this thing up here is like du dx, but du dx is going to be equal to du dy times dy dx. Is everybody cool with this?
So du over dy and then dy over dx, that's just chain rule?
Yeah,
Okay.
that's all it is.
All right.
So, just to reiterate this. We're going to say that u is equal to y squared. So d dx of y squared is like d dx of u, which we know is equal to du dy dx, according to the chain rule. So we know du dy is going to come out to be 2y. And since y is implicitly described in terms of x, we just leave dy dx as it is. Is everybody cool? All right. So, having said that, a good slide for y'all to check out will be this slide 50 in your week 5.2 notes. It just has a set of instructions for how to differentiate all of this, how to apply implicit differentiation. Having said that, I want to jump to a particular example. All right, we want to apply implicit differentiation to this giant beast. what this equation describes is this thing. We're gonna find the slope of every tangent line. We're gonna get an equation for the slope of every tangent line of that beast.
We can't see the slides.
Say what?
We can't see the slides.
Okay. Okay, the slide is slide 55 in week 5.2 notes. You can find those on Blackboard under exam 2.
Okay, thank you.
All right, so doing all of this very quickly, because we are going to do this very quickly. We've got y cubed plus y squared minus 5y minus x squared is equal to -4. We're going to apply the derivative to all of this. dx of y cubed plus y squared minus 5y minus x squared is equal to the derivative with respect to x applied to -4. This is going to come out to be 0, right? Some indifference rule says we can break up this derivative now to be d dx y cubed plus d dx y squared minus d dx of 5y minus d dx of x squared. All of this is going to be equal to 0, right? Well, we know d dx of x squared is going to come out to be just 2x, right? Using implicit differentiation here, we're going to get 3y squared dy dx. Three y squared dy dx. Implicit differentiation here is going to give us 2y dy dx. Here, it's going to give us 5 dy dx. Now notice, factor out a dy dx, and we can move -2x to the other side. So when we do that, we're going to have 3y plus 2y minus 5 times dy dx is equal to 2x. Now we can divide the polynomial for both sides. And we get that dy dx is equal to 2x divided by 3y. My mistake, I forgot to square on this, didn't I? 3y squared plus 2y minus 5. And comparing it, comes out to be the same. Having said that, you all are free to go. I'll stick around if anybody has any questions.